Welcome to the Foundry by Forge College. You know, today we're really rolling our sleeves up for a bit of mechanics inspection, if you will, to see if Cloudbreak's performance claims actually hold up in the real world. We've already talked about the theory of Solana state storage, but today we're bringing out the magnifying glass and the stopwatches. So let's just dive right into this explainer.
All right, here's our blueprint for today. We'll start with the need for numbers. Read the metric dashboard. Look at tail latency and amplification. Run a real-world DEX stress test. Build a load generator, and finally, translate that data into headroom. Let's get to it. Section 1. The need for numbers. Moving from claims to telemetry.
So we heard the whole sales pitch on Cloudbreak's memory layout in the last lesson, right? We know it groups accounts by owner and frequently accessed indices so that concurrent readers can pull relevant state without getting stuck traversing these massive monolithic structures. But now it's time to actually plug in the diagnostic tools and look at the telemetry. We have to translate those structural advantages into measurable signals because honestly, as engineers, we only trust what we can rigorously test and quantify. I mean, an architectural claim on a whiteboard is a lovely piece of modern art, but it's really only actionable when it's backed by hard numbers.
Moving to Section 2. Reading the metric dashboard, or what I like to call the 6 dials.
Notice how these 6 families of metrics map out our entire diagnostic dashboard. We aren't just looking at one single number here. We're looking at a rigorous, comprehensive picture. Starting from the top, latency percentiles tell us about our end-to-end request responsiveness. Next up, IOPS, or input/output operations per second. Well, those show us exactly how the storage stack is actually being used by the operating system. Then we have read amplification and cache hit rate, which prove if Cloudbreak's memory layout is successfully keeping that hot state accessible. And finally, throughput and resource utilization tell us about sustained capacity and exactly where our bottlenecks sit. We literally have to collect these at both the client side and the server side to get the full story.
All right, Section 3, tail latency and amplification. Let's look at the edge cases.
Now, you might be totally tempted to just look at average performance when evaluating a system, right? That's your P50 latency. Think of P50 as your average everyday drive to work. You've got your coffee, the sun is shining, the traffic is super light, it's pleasant. But P99 latency, that is your absolute worst case scenario. That's your drive to work during a massive unexpected blizzard, where literally every single traffic light is broken and, I don't know, you've just spilled hot coffee all over your lap. In real-time applications, P99 latency is what actually dictates survival. If Cloudbreak works as intended, we should absolutely see a massive drop in our P99 times due to reduced lock contention and much better organized reads.
Okay, so think about read amplification this way. High read amplification is kind of like needing to double-check a single sentence for a research project, but being forced to carry an entire incredibly heavy set of encyclopedias all the way across the library to your desk just to read that one single line. It's wildly inefficient. Cloudbreak aims to fix this by mapping on-disk layouts more directly to actual access patterns. So a lower read amplification score simply means fewer physical reads per logical account access. You just grab the one page you need and leave the rest right there on the shelf.
Which brings us to Section 4, the real-world DEX stress test. It's time to take this to the track.
So the really crucial point here is figuring out how all of this performs out in the wild. Let's say on a high-frequency decentralized exchange where tail latency directly impacts arbitrage opportunities. To do this, we set up a tightly controlled A/B test mirroring production. On one side, we have a baseline node. On the other, an instance using the Cloudbreak layout. We then replay live production traces against both of them. And as we constantly emphasize in our advanced courses at Forge College, testing in a vacuum is really just expensive guessing. You absolutely have to match your expected dataset size so your cache behavior numbers actually mean something. Now, during this test, you're gathering everything, right? Client-side latencies, server IOPS, page faults, CPU load, the whole shebang. But here's a pro tip. Make sure you tag your traces by request type. Ask yourself, are they account reads, account writes, maybe multi-sig transactions? Tagging these traces allows us to really slice the metrics by workload, letting us compare apples to apples when we analyze read-heavy versus write-heavy scenarios a bit later on.
Moving right along to Section 5, building a load generator to serve as your diagnostic tool.
Okay, so here is exactly how we build our diagnostic toolkit in Python. Step 1 is the setup. We bring in standard modules like asynchrono and AI HTTP for high-resolution timing. Step 2 is building the worker tasks.
We use consumer queues to completely decouple the generation of the payloads from their execution, and that allows us to efficiently push identical request bodies. Finally, step 3 is the execution itself. We fire those JSON RPC requests off concurrently, and we time the responses right down to the millisecond.
Once that queue is completely empty, our script calculates the stats. It basically converts the raw seconds to milliseconds and sorts them to find our P50, P95, and P99 percentiles. Honestly, what I absolutely love about this script is that it isolates the true end-to-end timing. By including server processing and network latency, it completely strips away the universal developer excuse to just, blame the network when that P99 latency spikes.
And finally, Section 6, translating data into headroom. Let's look at the final report.
Okay, looking at a concrete, real-world example of our A/B test results, you can really see what success looks like here. Under the Cloudbreak layout, our worst-case P99 tail latency drops significantly, from 120 milliseconds all the way down to 85 milliseconds. And because of improved locality, our physical disk reads, the IOPS, plummet from 18,000 down to 12,000. It's a huge difference. Plus, because hot state is fitting perfectly into memory, our cache hit rate soars from 72% up to 87%.
But remember, we are always looking for correlated signals of success across the board. An isolated drop in latency means absolutely nothing if it accidentally maxes out your CPUs somewhere else. If your P99 improves but your IOPS suddenly skyrocket, well, you need to investigate whether improved parallelism just shifted the pressure point to another part of your hardware stack. But a drop in P99 paired with lower IOPS and a higher cache hit rate? Wow, that is incredibly strong evidence that Cloudbreak successfully reduced the physical work required for the exact same logical operations.
So what does this all mean? Well, by combining these efficiency metrics, we can confidently declare our new capacity headroom. Because we've reduced the physical stress on the system, we can actually push a 1.5 times higher request rate before ever hitting our hardware IOPS ceiling. Think about that. We're serving the exact same latency service level objectives, but with 50% more throughput. That is exactly the kind of data-driven result you can take straight to capacity planning.
But of course, in the wild world of Web3, nothing is perfectly safe forever, right? Now that we've proven the speed and calculated our headroom, we have to question the safety. What happens to these beautiful, highly optimized metrics when this high-speed system actually crashes? How fast can it recover? Well, that perfectly tees up our next explainer on reliability and uptime benefits. To dive deeper into these courses and master the rest of this module, make sure to visit forge.college to learn more about this subject and other Web3-related topics. Thanks for learning with us, and I'll catch you in the next one.